Alright, I was going to try to make you guys a nice video where I talk really slow and go over things really slow, but my wife failed to inform me that Barrett's nurse was coming to the house this morning, and so now I don't have enough time to go real slow. I don't even know if this is going to upload by the time class starts, so I gotta kind of go quick here. And you hear my assistant next to me here, he's going to be helping me out. How's it going? You gonna tell him how to do this stuff? I already taught him everything I know, so he could help you if you need help. Yeah? Anyway, so here we go. First thing, we're almost gonna finish section 2.2 today. Remember the properties of limits we had? That was all the stuff where, like, if you have, instead of writing, I'll just explain it. The limit, as x approaches, don't write this down. As x approaches something and you add f of these things that you really like, and the limit as x approaches b of g of x equals 8, right? If you multiply them, you just multiply the limits. If you add them, you can just add the limits. All that stuff. Well, all that still applies if x goes to infinity. So it still works. And the reason this helps, the way we can use this, we can use it in a way we haven't yet. Now you can start writing. If we're trying to find the limit, say as x approaches infinity, of 5x plus the sine of x over x. So if we're trying to do that, and we're trying to do that without a calculator, it can be tough. But we can use those properties. And what we can do is we can break this apart. So what I mean by that is, if we have 5x plus sine of x, these are both divided by x, right? So I'm going to break these apart. So this is the same as 5x over x plus the sine of x over x. Right? Because if I added those together, I'd get that. They already have a common denominator. Well, now I can simplify this. Well, 5x over x, that's just 5. So I got 5 plus the sine of x over x. Don't try to just eliminate those. So what that allows me to do is, if I do the limit as x approaches infinity of this is the same as this, and this is a lot easier. Well, what those properties allow me to do is I can break this apart now. I can go the limit as x approaches infinity of 5 plus the limit as x approaches infinity of the sine of x over x. Right? Because if I add the two limits, I just add these together, and it's the same as if I were to do that, or eventually do that. I just broke it down and made it simpler. So the limit as x approaches infinity of 5, well, that's easy. That's just, 5 is just a line at 5, so as x approaches infinity, it's still going to be 5. Do you agree? Yeah? He says he agrees. Sorry, I'm distracted. And this one, we've done this one before. This was from sandwich theorem. Remember? Sine of x, biggest it could be is 1 over x, and the smallest would be negative 1 over x. The limit of infinity of those is both 0, so this one is 0. So we have 5 plus 0. Just kind of remember that one. So the whole thing, your final answer is 5 for that. And we can do that without a calculator thanks to those properties. And I'll do another one here in a minute using those properties. But I want to talk about something else first. Well, a couple other things first. Next, vertical asymptotes. Remember the horizontal asymptotes? You just find the limit as x approaches infinity of whatever your function is, and if you get an answer that's not infinity, that's where your horizontal asymptote is. Well, now for vertical, just think, let's say you have a vertical asymptote, it's going to go up like that. if you take the limit as x approaches some number from the right or from the left, it doesn't matter. If your answer, the limit as, so like here, if I'm going as x, here's c, if I'm taking the limit as x approaches c from the right, if my answer is infinity, then x equals c is a vertical asymptote. Right? Or if you get negative infinity, you could do the limit as x approaches c from the right. If you get negative infinity, you'll get that's a vertical asymptote. Or you could go from the left too. That could be a negative. So an example of that would be like if I find the limit as x approaches 0 from the right of 1 over x. You should know that one. That's 1 over x. That's just like this, right? So the limit as x approaches 0 from the right. As I go from the right, I go up. Oh, hey, it's just going to keep going up and up and up and up. Closer I get to 0, it's infinity. That tells me that x equals 0 is a vertical asymptote, which we know on that graph it is. We also could have done the limit as x approaches 0 from the left. We would have got negative infinity. That still tells me x equals 0 is a vertical asymptote. And I'm going to do some example problems here in a second. After we talk about end behavior models, so end what an end behavior model is, basically, is, let's say we have two functions. Like I'm just using the book example here. This is on page 73. I have 3x to the fourth minus 2x to the third plus 3x squared minus 5x plus 6. And I have another function, just 3x to the fourth. These two functions are very different. I mean, this one's 3x to the fourth plus all this crap. This one's just 3x to the fourth. And if I look at the graphs of them, that big one right there is 3x to the fourth. The blue one is that one there. So, I mean, they're different functions. But what I mean by end behavior is, as you go out to the ends, or as x approaches infinity or negative infinity, if you think about if you zoomed way out on the graph, those two functions look almost identical. And you can do this on your graphing calculator. And if I had more time to upload, I would do it and show you. If you graph both of these, if you look at a standard window, they'll look very different. But if you zoom way, way out, you won't even be able to tell a difference. What that allows us to do is easily find limits as x approaches infinity. So, yeah, that's what an end behavior model means. This will make more sense when I do some examples. So like the example they do here in the book, it says find the limit as x approaches infinity of this whole long thing. Uh-oh.